make introductions. So I think we all, almost everyone probably knows Amal. She's a professor at Northeastern University. She's just been doing a lot of great work in many different topics that are very dear to everyone in the PriSC community. And she also did a great job as a program chair of POPL this year. So yeah, she's going to talk about semantic intermediate representation for sound language interoperability. Really looking forward to the talk, and the floor is yours. Take it away.
Okay, let's just see if the clicker works. 1 second. Yes, we'll be fine. All right, I just have to not walk into the screen. That's the key challenge. So hi, everyone. Today I'm going to talk about sound language interoperability. I was sort of going between, am I talking about sound language interoperability or secure language interoperability? You can figure out which one it means. But I think that most of the ideas that I'm going to talk about really apply to secure interoperability as well. But specifically, since most of my case study and stuff is about soundness, I went with a more conservative title. Okay, so I haven't said what semantic intermediate representations are. That'll come up a bit later. So basically, this is the secure compilation workshop and principles of secure compilation. And I'd like to talk about, how we need proof frameworks in order to do much better in the space of language interoperability, to actually prove foreign function interfaces are sound or secure, and so on. Let's just sort of start at a very high level. Type soundness, right? In theory, you have languages like, let's say, ML, Haskell, Java, and what PL meta-theoreticians do is they go, at the very least, verify type soundness of at least a core of the language, and usually via progress and preservation. But of course, then when someone goes and implements these languages, whether it's OCaml or GHC or Java, that's when you're no longer working with just the core language for which you've proved type soundness. So in reality, we almost always implement some sort of a foreign function interface, right? So this is where an implementer of the language immediately, in order to develop a practical implementation so that people can actually write practical code in the world, has to sort of allow for these escape hatches, if you will, right? I call them escape hatches because they're escape hatches from the type soundness theorem, right? Now, what your OCaml code is linking with, if it's linking with C, you no longer have a type safety guarantee, right? And this is one of those problems that we haven't really addressed, right? We don't have good, ways of verifying such FFIs, any kind of interoperability between languages. When it comes to the actual implementations, we kind of ignore it. We just hope for the best, and give programmers all sorts of best practices to use so that everything kind of goes okay. Okay, so what we need, I would say, is for working meta-theoreticians, or you can call them the verified compiler writers, hopefully they should do meta-theory of languages as they are implemented, which means that you have to take language interoperability into account. So what are the techniques that they can use for soundness of the original language plus the interop that they are actually allowing for via their implementation? So that's what this talk is going to be about. Let's just kind of look at a few, examples. Like basically all languages support interoperability, right? There's CFFI, comes with tools like Swig to generate wrappers. OCaml has C types. Haskell has inline C. Java has the JNI. Rust has bindgen. And then there's a different form of interop between languages that all target the JVM. Right, so you compile from Java, Scala, Clojure, Kotlin down to the JVM, and you do interop at that level. Very similar sort of pattern again going on with the CIL, interop between the .NET languages, such as C#, F#, etc. They all compile down to the common intermediate language, and that's where interop happens. But how do we really prove proper soundness of interop between the original source languages? Okay. So there's been one approach to this, which needs to be mentioned. I think that this is a seminal paper. So this was POPL 07. Jacob Matthews and Robbie Findler said, we have a lot of interop in the world, and we really aren't talking about it. How do we prove it sound? And so they developed this this framework, in a sense, of multi-language semantics, where they gave a recipe. In the paper, they did this for what looked like a core of ML, a typed language, and a core of Scheme, an untyped language. But in general, they basically gave a recipe for, you can take a language A and a language B, a red language and a blue language, if you will, and take all the terms of the original languages and then add two boundaries, right? So you can add an AB boundary, which allows you to embed blue language terms into red language contexts, and vice versa, red language terms into blue language contexts. And once you've done that, they gave typing rules for these boundary terms. So not, you can't have, you have a certain restricted set of red and blue types that can appear on both sides of these two boundaries, and then you give typing rules for them. Because, conversion between it doesn't make sense to convert up between absolutely everything. And then they gave a type-directed operational semantics. And the idea here was, how do you run one of these boundary terms? Well, if you have a blue term here sitting underneath a boundary, so sitting in a red context, you basically just keep running the blue term using the blue language's operational semantics. Don't do anything different. But when you hit a value, that's when the interesting thing happens. So the boundary semantics were all these reductions, which were the interesting bits of the multi-language semantics, which do a conversion from whatever particular, a type-directed conversion from the blue value to a red value, and vice versa. Okay. So, and here, if you have a number 5, you might convert it. If you have Boolean, if you have binary in the other language, you might convert it to 101. But if you have functions, that's where the idea from higher order contracts came in. You essentially wrap it in the other languages' functions. Okay, so that was multi-language semantics, and it's all about taking two source languages and putting them together and saying, how do we expect to convert at these boundaries? And then, once you have this, the multi-language is just a gigantic language, a standard language, typing rules and operational semantics, so you can prove type soundness using just standard progress and preservation. So this was very nice. And it's been used a lot. Lots of people have used it. I've used it extensively in my own work. So in interop between multi-language semantics for simple independent types, between unrestricted and substructural types. We did a paper on high-level functional language interoperating with a low-level assembly, a typed assembly language. And then I've used it in various compiler correctness results where the multi-language semantics is between a source and a target of the compiler path. But basically, this whole multi-language semantics approach, it stays at the source level. And that's not how FFIs are implemented in practice, right? That's not how the code that we run is. Like what I would like to do when I said working meta-theoretician, I would like for people who, let's say, do verified compilers for a living, right, to also be able to verify the FFIs that they're implementing as part of their compiler. So how do we, at a 30,000-foot level, how do we implement interoperability in practice? Well, so you take the source code from the original languages and you compile it down to a target, and that is where interoperability happens. It happens after compilation to a target language. And as part of this, we usually implement some glue code that goes and does conversions between the data representations that you get after compiling from the two original source languages. So it's a story of interoperation after compilation, right? And that's the thing that the multi-language semantics doesn't support. And that's why I'm at PriSC talking about it, because it's about compilation. Okay, so what we need and what I'm going to talk about is really a framework for design and verification of sound language interoperability and also secure language interoperability. I'll talk about that towards the end. That's connected to the implementation, that's connected to the compilers, right? Okay, so let me say what the approach is with these semantic intermediate representations. So here's a recipe, the framework that I want to show you. So you have an original language A and a language B. Throughout this talk, I'm going to talk about two languages that are both typed. Type sound interoperability is what I'm after. Of course, one can be unique typed. That's fine. Okay, so then what do? You, the language designer, needs to go off and add certain boundary forms so that you can actually allow interop between the two languages. Okay, so here I'm just, instead of writing A, B, BA boundaries, I'm just putting colored brackets around them for this talk. And what this says is that, this is a B language term sitting in a boundary, and the context wants to treat it as something of type tau A, and vice versa. Okay, but now the next thing that I, the language designer, needs to make some decisions about is what do I want to allow on the two sides of the boundary? So, I can do this via my typing rules. So when I do boundary rules, I want to say that an E of tau B can be put inside a boundary with a tau A on the outside if convertibility is allowed, is sensible between a tau A and a tau B, whatever your tau A and tau B might be, right? So really the decision we're making is, what are the types in this language that even make sense to convert to the types in the other language, and vice versa, right? And we're making this decision, implementers right now are constantly making this decision, even if they're not giving you a typing rule for it. They're just going off and then implementing the glue code for it, right? So these decisions are already being made, just sort of making it a little bit more formal in the framework, how to pull that in. Okay, so we make a bunch of decisions about what can be converted to what between the two languages, right? You don't want to convert a function to an integer, or an integer to a function. That's worse. Okay, so after you specify your convertibility rules, you implement the target level conversions for each pair of convertible types. I'm going to write these as a C, a conversion that takes a blue type to an orange type, and one that takes an orange type to a blue type. Okay. All right, so now I have these rules, and I have implemented some conversions in, in target level code. Okay, so now what do we want to do? Well, we want to prove the conversions sound, right? To prove soundness of the conversions, what we're going to do is define this thing that I'm calling a semantic intermediate representation. And basically the idea is you want to say what the meaning of your source types in each of the languages should be. Okay, so we're going to do this using a logical relation. For this talk, my logical relations are just going to have one term in them. You can do binary ones, but digression. Okay, so we're going to define the meaning of source types as sets of target terms. Okay, what are all of the target terms whose behaviors are kosher with respect to what my type should mean at the source level, right? And of course, there's a compiler intuition involved here, but this relation is not pulling the compiler in. I'm just giving a specification, if you will, of what target behaviors make sense for every single blue source type and for every single orange source type. Okay, so once I've done that, basically, I just want to show you this picture. What we've done is we've effectively said, I mean, really, we have two languages, but I'm just showing you one here. If we have this orange language and it has a bunch of types, then we're saying each one of these types is inhabited by a set of target terms. And in doing so, we're basically defining a big logical relation, which actually, I'll also have blue language types that are circles in here. But what I want to point out is that what we've done is we aren't allowing the entire target language or the entire IR, at this level, to be part of the logical relation that we defined. It's actually cut down because it's sensible somehow, right? It's the sensible behaviors that inhabit our source types. So the semantic IR is like this sensible subset of whatever, of the entire IR. The entire IR can have a lot more junk in it. Okay, so this is a spec where we're sort of defining this circle by giving a logical relation. Okay, so once you have that, we're ready to prove the soundness of conversions. So anytime you have a rule that a particular blue type is convertible to an orange type and vice versa, you have to prove two lemmas, which is that if you take any target term that inhabits the blue type, if you apply, and this is target code, if you apply your conversion, also target code, then this term, the converted code, behaves like the orange type. So it's satisfying your spec, and vice versa. So just take the behaviors and show that they properly belong in the right behaviors for the type that I'm converting to. Okay, and once you've proven conversion soundness, you prove the rest of the language sound using standard fundamental property of logical relations. This is the hardest part, the part we don't know how to do, right? So that's the interesting bit. And once you have that, you can prove the soundness of all the regular terms, typing rules, as well as for the conversion rules. Okay, so that's the recipe, right? So I just want to say that this, the stuff that I'm talking about is all in our PLDI-22 paper, where we did 3 separate case studies. I'm going to show you one of those, but let me just say what case studies we did. So yeah, and this paper was really about a framework, right? Just kind of show that interoperability, we can support interoperability between different flavors of small languages. It doesn't contain a very gigantic real case study yet. Okay, so the first one we did was we took a look at shared memory interoperability and this issue of data representation. So in particular, it has examples of when is it safe to share a mutable reference. Both languages have mutable references. When is it safe to share them across languages without any copying or wrapping, right? Like, when is it okay for me to convert a ref of blue tau into a ref of orange tau? And essentially, it's when the blue tau and orange tau under the references have the exact same inhabitants. Then you don't need to wrap it with anything. It's just free, right? And these kinds of things, the semantic model kind of shows language designers when they're going to pay a cost and when they're not. And I think it helps make a lot of decisions. Like if you find that conversions are going to be extremely expensive, you might not want to implement them. So you can restrict your convertibility rules, perhaps, and say that certain things are not allowed. You can do that. Okay, the second case study was between an unrestricted and affine language, essentially a mini ML, and something we called AFI. This is the one I'll go into later. This was safe mixing using the affine language, you can only use affine resources at most once, right? So we used runtime checks to ensure that that was in fact the case, that you cannot use an affine resource more than once. But then we also made sure that the dynamic checks are only performed when you don't actually have a static assurance of affine use. I'll explain what I mean by that in a little bit more detail in a bit. Okay, and then the last one, and this was really the coolest one in my opinion, but it's too much to talk about in a talk, so that's why I'm not talking about it here today. It's between essentially an ML-like language and L3, which you can think of as like almost like a core essentialized version of a Rust, because it has it has a type system for safe strong updates. So basically, this is a GC language, and this one is a manually managed language. Sorry. A language with manually managed memory with safe, strong updates. It has this idea of linear capabilities. Basically, in order to free a location, you need to give me the linear capability. To read from it, you need to give me a linear capability. I will give you a new one back. Similarly, to write to it, that's what you need to. So we had sort of an axiomatization of a garbage collection step and so on, and we showed interop between those using this recipe. Okay, so let's dive into a bit more. And if you have any questions, it's a workshop, so feel free to interrupt. Yes, Andrew.
So when you were talking about these conversions earlier,
yeah,
it seemed to me that you didn't really have any explicit representation of the kind of runtime state. So you brought up mutability more recently, and so clearly there is some state potentially hiding behind the scenes. And I guess I'm just wondering, it feels like there must be some extra pieces to the formal sense.
Yes, so the question is at the target level, right? So when you have a mutable reference, at the target level, you're going to have a location, right? It's pointing somewhere in memory. The logical relation we set up will have a world which is describing shapes of memory, and then the inhabitant of the mutable of the reference type will be a location paired with a world. You'll see this in a little bit because I have mini ML. Yeah. Okay. Yes. So state is very much there, and we very much care about kind of shared memory interop between these languages. And that first case study, even though it was small, it does exactly that. Okay, so for mini ML and this affine language AFI, mini ML, we have a polymorphic language with references. So we'll talk about those in a bit. And the rest is completely standard, standard typing rule, type variables, and term variables. Our affine language, AFI, has unit int, it has linear, affine function types, and it has bank types, additive pairs, and multiplicative pairs. So, these are affine pairs and these are just additive. And the form here is that for the additive pairs, you can just project out the two things from the pair. For the linear pairs, you have to do the pattern matching. The interesting bit is that we also have the boundaries that I was showing you before. So we add them to the two languages. And just to mention here, gamma has usual term unrestricted variables, and the omega here I'm going to use to keep track of my affine variables. Okay. All right. Now I need a target. And again, I'm going to keep this very high level. This is not, an assembly target because you would get lost. So I'm going to compile those two languages to this lambda calculus VM, if you will. But it has locations and everything else that an untyped lambda calculus would have. And I kept this, we kept this untyped, is particularly because most target languages are untyped, right? So it at least gets that use case. We've added, we have references, of course, and we've added fail. And I just want to draw attention to one thing here. We can fail with a type error, saying that something, type-like has gone wrong. The kind of errors you might, runtime type errors you would get in Scheme. But we also have these conversion errors, and I'm going to use the conversion errors later. So basically, I'm going to say that my interop is sound if I have 0 type errors, but I do have conversion errors because those can be allowed. All right. So AFI typing rules, just to make sure you're following the affine bits. Affine things go live in the omega environment. These are unrestricted variables X. They live in the gamma environment. Otherwise, this is completely standard. The only thing to point out is that anytime you have an expression with two sub-expressions, you need to split the affine context when type checking each one of those sub-expressions, because you can't use them more than once. Okay. Let's talk about what the compilers might look like. So here's where things, well, mini-ML is kind of straightforward. Okay, so this compiler, we're just compiling from typed mini-ML to essentially an untyped language, so it's really mostly straightforward. You know, I'm not really doing anything. I'm just erasing types, for instance, right there, for polymorphism, and annotations on those. And then we have to figure out how to compile the boundary terms. And that's exactly where these glue code, the conversion code that we're going to implement in the target language can be used. So here, if I know that my orange E has type orange tau, I use that particular conversion function and wrap it around the compiled code. Okay, and then the AFI compiler. This is much more interesting. So here we have to be careful. This is an affine language. It's being converted to an untyped lambda calculus, right? We need to make sure that the affine resources are not used more than once. So the compiler is going to use this trick that is going to wrap anything that is an affine resource in a thunk. And within that thunk, there we'll allocate a reference, and the reference will contain a flag. And that flag will tell us whether or not our affine resource has been used already or not. Okay, so if it has not been used, you return the affine resource to whoever wants it. But if it has been used, you want to fail. So essentially, what's the thunk doing? It's allocating a new fresh reference, saying initially the flag is set to unused, and then it's returning this thunk. So if I want to use whatever the affine reference, whatever the affine resource E is, I will have to apply the thunk to unit. And then if the flag is true, then that means that it's been used already. So I will report a conversion error. Otherwise, I will set it to used and return the resource. Okay. This is going to come up again and again, so I just want to sort of say what it does. All right, so how do we use this? The compiler is just going to, in the case of affine application, we're going to make sure that our argument, which is going to flow in, right? It's going to flow into a function that is expecting to use its argument at most once. So we're going to make sure that we take the E2 and put it in a thunk, and then pass it to the E1, to the function. And similar thing is happening over here because these two are affine variables. So we need to make sure that whatever this E is right here, that we take essentially its first and second and put it in two thunks. Yeah. Yes. Oh yes.
So you have the static language
Mm-hmm.
that you compile using these dynamic checks already.
Yes.
In preparation of the sound
In preparation of
interoperability,
the
right? Since if you
interoperability.
were to just compile this language as is without interoperability, you wouldn't need to do the
Yes, if you were
reference
assuming
trick.
absolutely zero interoperability, then you wouldn't need to, right? Because then you're assuming that you're only linking with, unless you're assuming that you want to allow linking with arbitrary untyped code, then you would still have to do this, right?
So this is a possibly related question, which is, do you have a slide coming up which has got the type rule for how, in particular, the affine context gets generated when you move from the non-affine world into the affine world?
I think I have what you want,
Okay,
but
good.
if I don't, ask me again.
I'm just being impatient.
That's okay. I'm going compiler first and then rules. So yes.
I also
Yes.
have a question. So, is there a way to, if you can't type something, instead of keeping the reference, just having a refinement type or some sort of theorem that someone can prove, and then you can remove the dynamic check?
If you can't type something, that's what you said at the beginning?
Yeah. Then emitting like a proof obligation that if you can prove this, I can remove this dynamic check or something along these lines.
I have something like that, which I will show you. So right now I'm just talking about ML AFI interop. assuming dynamic checks everywhere. But at the very end of that, I will show you how we can do better.
Okay.
When we know that the affine resources, when we statically know that the affine resources cannot be used. We've done that. The PLDI paper actually has that in full view.
Okay, great. Thank you.
Yeah.
I'm also wondering, so you're throwing the conversion check here, even though I would have,
Oh, the conversion error, right?
yes,
here?
yeah,
Yes.
the conversion error here, even though this is something that should be handled by AFI's own type system. I would have thought that would have been a type error, but I'm not sure. So when would you throw a type error?
Yeah, so this is kind of related to Kathleen's
Yeah.
question, right? That I'm anticipating the interop and therefore compiling in this way. So anticipating the interop, I think the best decision to make here is that this should be a conversion error, because you know that it's happening, or at least it should be called, maybe it shouldn't be called conversion, maybe it should be called interop, because this is the kind of error you would still want to compile this way and throw this error if you were interoperating with just arbitrary target code, right? So from that perspective, this is kind of saying, hey, there's code here that's trying to keep the affine resources safe, and something has gone wrong, and it's gone wrong because of interop.
I had a general question about the calculus. Would it work if you added lambdas that take ordinary variables and not affine variables, or is it just for to keep the presentation minimal?
If I have lambdas that only take unrestricted variables?
Yeah.
Yeah, so here, like we saw right in the slide before, the ML compiler, which has only unrestricted variables, nothing interesting is happening, right? No thunking required, because there aren't any concerns about affine use. This is the AFI compiler, and in fact, we have lambda x.e in the AFI compiler. I just left out a couple of lines of the compiler because this was the interesting case, and the other one doesn't do anything, right? Because lambda x, we don't need to protect the x. All right, so that's
Wait.
Oh, yes, sorry.
Just to make sure, because so far you said about the conversion function, the last rule,
Here,
right,
this
which
one?
is supposed to do the conversion between the two worlds.
And I haven't really talked about this
Exactly.
yet, right?
And instead, you're talking about thunk here, which is outside. Like, I would expect the thunking to be inside the definition of C, right? Because that's where the boundary is
C
happening.
will also use it.
Ah, okay, cool. But you're talking about this, right?
Yes.
Excellent.
Yes. Okay. All right. So now we have to decide what convertibility rules we want. What can be converted to what? So let's start with the simple ones. Unit in AFI can totally be converted to unit in ML and vice versa. It's a no-op, right? So we're going to allow unit-to-unit conversion. We'll talk about how these are implemented later. Here, I'm just showing what conversions I want to allow. It would be nice to allow the multiplicative pairs to be converted to the ML pairs, right? So we can do that. Tau1 tensor tau2 can be converted to tau1 paired with tau2 if the tau1s are convertible and the tau2s are convertible. Okay, these are simple rules. Now let's get to the hard one. Oh, sorry. Let me show you the conversions before I get to the hard one. So unit to unit is just nothing, right? We don't need to add any kind of glue code or conversion code. For pairs, we just kind of recur and use whatever conversions are we need for the tau1s and the one for the tau2s. Now, functions are the hard case, right? How do you talk about convertibility? And here what happens is you have to allow affine functions to only be interconvertible with ML functions that expect the thunk as their original argument. And that thunk is essentially hiding the resource of type tau1, which you can think of as the counterpart of this affine resource, inside that thunk. Okay? And so now if we drill down and ask the question, all right, if this is your assumption, right, and this relies on the tau1s being convertible and tau2s being convertible, that's sort of straightforward. So if this is the convertibility you want to allow, how are you going to implement it? So this now uses the thunks that you were talking about. So if we want to convert from an affine function to this ML funky function, what do we do? Well, so here's the target code E that really should be should essentially morally have the type tau1 lolly tau2, right? It's an affine function. So I'm calling it X, and then I'm basically X gets used here. Okay, so then what we return is a thunk. This thunk has to be a unit arrow tau2 thunk, right? And what we're going to do is we're going to, apply it to unit, get out a blue tau 1, convert it to an orange tau 1. That's this xconv. And then we are going to func the xconv and feed it to our function, which has that type, right? What we get out after this function application should be a tau 2, an orange tau 2, and we convert it back to a blue tau 2. Did everyone follow? There's higher orderness and funking going on. I know there's multiple things, right? And then in the other direction, what are we doing? Well, we're taking something that is of this type, essentially, and trying to convert it to an affine, target code that implements this affine thing. But remember, our affine functions need to take these linear resources. Need to take protected func resources. So what do? We take our x and let me see. We want to return func in the end, which is how this code is going to be represented at the target level. And what do we do there? Well, when this code gets an argument, morally speaking, a tau 1 func, then what we're going to do is we're going to apply it to unit. We get out a tau 1. We convert it to the other one. We func this thing. Right now, this is the blue tau 1 getting funked and getting fed into the original x, which was the code that we had. Okay, and then convert back. Again, convert forward, convert back, right? The higher order contract-like application. Sorry if there's a lot going on. There's a lot of thinking going on in here. Yes. Microphone.
Okay, so what stops some blue code? Because blue code could call the func and copy the result.
Blue code could call the func.
I mean, it's just an arbitrary, like, non-affine program of type unit to tau 1 to tau 2. So it's perfectly entitled to do copying on anything it likes.
This is what func is. It fails, right?
Yeah. No, I mean, you unfunc it once.
Okay, so you
then
copied
copy
it.
the result of unfunking it.
Yes.
So is there some deep funking that's going on that makes sure that everything that's affine is nestedly funked?
I think the entire compiler, right, all of the places where we are inserting these funcs does exactly what you just said, right? This deep kind of making sure that no resource is ever getting used multiple times, right? Intuitively, that's why the funking isn't just happening in these two conversions. It's already happening here as well. Am I saying the right thing? I need to think about that a little bit more, but I think that's right.
Like you need to use the func in a specific way, and you're not generating all the black code. You're just generating the black code and use the funcs directly without doing the replication that he's talking about.
Yes, I mean, you're generating black code. You're only going to, for the purpose of this case study, I should say that you're only interacting with other black code that you generated. So you generated black code from orange language and from blue language, and that's what's interacting. That's it. So you're not. So this is not about, like robot safety is about arbitrary context, right? This is not that. The framework is not allowing for that. I'll talk about that at the end.
So if there was some, I mean, I think one thing that would help would be if there were some base types that you actually cared about the affine use of. So something like capabilities.
Yeah.
So is there an invariant that's being maintained that blue code never gets capabilities? It only gets funked capabilities.
That's a good question, but can I think about that offline?
Anyway, yeah,
I'd love to do it afterwards.
I'm inventing
That's a really good question.
problems.
Yeah. I would love to throw that in and think a little bit about what we would need to do. Okay. Shall I go on?
Hey, thanks. Just I guess a very shallow question. Like it seems like the two are kind of the same code, or am I missing something? Is that coincidence?
They're both going back and forth, but other than that, they are, in terms of representation, they are, right? The representation of this is basically what this is morally saying is that the representation of this is already kind of that, right? That you're representing the arguments of these orange functions as functions.
Yeah. So I guess I just meant because the upper code is written with one let binding more, but otherwise, like if you unfork that one lit binding, is it the same as the lower code, or like except for the
I mean, it
conversions,
shouldn't be
right?
exactly the same,
Okay.
but we can
Okay.
think about it. And the one thing I
Yeah,
want to
okay.
point out is maybe we go back to the compiler here, right? Like, so this orange code is getting just compiled to something that says I take a lambda A, right? I'm not doing anything here, but the assumption is that whatever A you pass me will be funced,
Okay.
right? So the representation on both sides is essentially a unit arrow tau1 type
I
of
see.
representation.
Okay. Yeah.
And
makes
that's
sense.
why you're noticing the similarity.
Yeah. Ah, yeah. Yeah.
Mhm.
Thanks.
Okay. All right. Next step, we need to define the logical relations. How do we do that? It's a logical relation that's indexed by the source types, and it needs to be inhabited by target terms, right? So the shape of it is going to be for both the blue types and for the orange types. They're going to be inhabited by target, the value relation is going to be inhabited by target values paired with a world. I'll talk about it in 1 second. And similarly on that side, there will be an expression relation, etc., as we normally have, which says when does an expression of target expression belong to the blue or the orange types, behave like them. So what are the worlds doing? Well, the worlds, so this is a step index model. It just has a step index k. It has a heap typing, which keeps track of, in essence, it keeps track of all the ML references, right? Because our mini ML has references. So it basically says, oh, location L, ML reference should have this type because ML only allows type preserving updates. So this needs to keep track of what type you can store in those locations. This is the interesting part, A. So in the world, we also keep track of all of those reference cells that are being allocated by those thunks, right? So I'm going to call them flag reference cells. They're references that contain a flag about whether an affine resource is still unused or if it's been used, right? So A is a mapping from the locations that get allocated when we allocate a flag reference, and for every affine resource. And what they keep track of is essentially this is a Boolean, which is used or unused. Okay, so what if you have any L equals B in this set A, then it's saying that the flag is B, or used or unused in the current world. And how do we then define, what future worlds we can move to in this logical relation? This is a Kripke logical relation. So we can say that this is a valid future world of this one. If, in the future we have fewer steps, standard, the type that you store in the heap typing never changes, standard. But the interesting bit is for the affine flag references, once you have set a flag to true, which means used, you cannot set it back. So in the future, used must always remain used. You can go from unused to used and never back again. That's it. Okay. So and the rest is fairly standard. I don't even really need to go through it. Target integers inhabit both of those int types in both languages. Target pairs inhabit, the pair types if the components inhabit them. Functions is the standard thing. A function at the target level inhabits tau1 or tau2. If in some future world you give me a value of type tau1, I plug it in, I get some behavior or term of type tau2. Yes.
Is there a technical reason for having a separate heap for the flags?
Separate heap
A
for the
separate
flag?
heap for the
Oh
flags?
yeah, I mean yeah, I would say so. So it's not that the heap is separate; they're all in the same target heap. The L's are all the same. Yes, but semantically in the worlds, I'm keeping track of them separately, exactly because when we move to a future world, right, and we have more of either these locations or these locations, what are the rules about which worlds we can move to? Well, for these locations, the rules are that, this is a mapping from locations to types, and this is a mapping from locations to used, unused.
So to types, syntactic types.
This is, no, it's semantic types.
Semantic types. Okay, then,
Yes,
then you can.
standard.
Yeah,
This is, so if I leave this out, this is the model of ML that we are,
exactly. Yeah.
that's in my dissertation, right?
Exactly.
2004, like we know how to do that part. So
Yes.
this is the extra bit that we're adding.
Yeah, but why couldn't you keep track of that just in the semantic heap side?
Because I don't need, because the invariant on those locations is not that I can't change the type. Okay, let's say it is. But in addition, I also need to make sure that I can only change the contents of those references. I can only change the flag from unused to used. I can never go back from used to unused. That's what this part is saying. In a
Okay.
future state, right? So this A
Yes,
prime
yes.
is a good future of this A. if whenever A of L is true, meaning used, then A prime of L is also true.
I see.
You cannot set it back to unused.
No, I see.
So
Okay.
it's very different invariant that we need on the flag references compared to what we need on the ML references.
I see. Thanks.
Okay. Now. Okay, so once we've done all, oh no, I didn't show you that, did I? Where was I? I was here. Okay. So this is a slightly different plunk. It has two parameters, but let me just walk through it. All right, so next we have to say what are the target functions that inhabit the affine types. Again, kind of standard in some future world, if you give me an argument that inhabits tau1, what do I need to do now? These are affine, this x that I expect here is going to be this value that I get. I need to treat it as an affine resource. So what am I going to do? I'm immediately going to take the world that I'm in, W prime, and I'm going to add a new flag to it, a flag reference to it, and say that initially it's false, meaning unused. Okay? And then in this particular world, which now has an additional flag reference for my argument, because it's an affine thing, that's where I'm going to now, I'm going to put it inside a thunk, which does the same thing. Here's my new flag reference. Here's where I'm using it in my thunk code to say the same fail kind of thing. And then I basically go plug in this thunk into the body of the lambda and go run, and I should get something that behaves like a tau2. All right, so semantically do exactly what we are wanting to do operationally, right? But we have to capture that. Okay. And then finally, just the last thing to show you, some target code E inhabits either a blue type or an orange type. Think of this as I have two E taus, one for blue, one for orange. If you select a heap that satisfies the world and you run for a certain number of steps, then either you report a fail conversion, no fail types allowed, right? But you can fail with a conversion error, no type error, or the standard thing where we have now reached a heap that satisfies an extended world, and the result that we have is a value of the right type. Yes. Say that again.
On the first line, you said there's fail. Should it
Ah.
Fail com or fail type, or is that what fail is that?
Let me think one
Or am I
second.
not remembering that?
It should say fail conf. Sorry.
Okay.
Missing
Yeah,
typo.
that makes sense.
Totally. Yep. Okay, and then you kind of do the standard practice. You say what the semantics of the top level typing judgments are, and the only extra thing, I'm not going to show you that, but the only extra thing you have to make sure when you give this semantics is that all of the affine values that you substitute for the variables in here, this semantics will have to make sure that they're wrapped in a thunk with a fresh flag reference cell that is set to unused, and then you're off. Standard, yeah.
Can stay here with them.
Mike, just give it to that part of the room.
We'll just hang on to this. Okay, why are the two typing contexts in the blue code? I understand why they're there in the orange code.
These are alphas, type variables, and these are x's. Yeah.
It's,
So
it's
this
not
is
a linear,
ML.
non-linear
It's
split.
system F.
Good, right.
Yeah, with references.
In which case, so why aren't there three in the orange?
The orange language itself doesn't have type variables. Oh, and you've just touched upon a decision we made, which is that you can't bring type variables over. Okay. Oh, yes.
So earlier you said that conversion failures are fine, but type failures are not fine.
Yes.
Where are type failures thrown? Because we haven't seen them.
Okay, so
yet.
our target language is basically Scheme, right?
Okay.
And Scheme throws runtime type errors all the time, right? But we are compiling from two statically typed languages down to this Scheme, if you will, right? And we're saying that because the original languages were statically typed and we're making sure that their interop is good, because there's interop, there will be failures with conversion errors, right? Or interop errors, we can call it. But there will never be fails with type errors. So in other words, you don't get any runtime type errors the way you do in Scheme.
Got it. Thanks.
It's a very interesting thing having to think about these little subtle things, like, what kind of errors, are possible or not, because all sorts of runtime errors are possible in a target language. But our task is exactly to say that we had all these beautiful static guarantees at the source. we want to set up these semantic IRs, these logical relations, to say that we still have those guarantees. We don't want to lose them. Okay, so with all of that, I've shown you all the pieces, right? We specified the convertibility rules, we implemented the conversions, we defined this, I roughly showed you the semantic IR we defined, and then we can just go ahead and use all of the things that we've set up to prove the conversion soundness lemmas, and then finally prove the fundamental property in type soundness. Okay? All right, how am I doing on time? Maybe not great. I just want to talk quickly about the thing that I've shown you so far. It's a bit naive. So sound interop, as I've shown you so far, has a runtime cost, right? All affine bindings have to be checked on use. Okay. The sad part is that an entirely affy function compiled using what I've just shown you would have the same runtime checks, even though the type system statically guarantees that they are redundant checks. So how can we do better? Here I'll just show you, just give you a hint of the idea, but the details are, the PLDI case study is actually this version, not the simplified version I've been talking through. So we can do better if we make a distinction between what I'll, in air quotes, I'll say, our dynamic affy functions, those that are at some point passed to the ML side, where they're threatened. They could be used multiple times. And I'm going to mark those with these circle things. And then there are these static, luckier affine variables, which are never passed, and functions which are never passed over to the ML side. So we're not worried about wrapping, having flag references for them. So I'll mark those as these, and you can do a sort of inference to figure out which ones are which, given a program. But we don't do that in the paper, but we say, you can make this distinction. And once you've made that distinction, what your compiler should do is it should compile these static affine variables without any extra wrapping or thunking around them. Just standard, they're safe, because they're never going to be passed to the other side. They're never going to interact with in an environment where they're threatened. So with this distinction, how do we actually prove this soundness? It actually ends up being quite interesting if you look at the semantic model. You need a more sophisticated semantic model to show that this all works out, because it is kind of a, it's tricky. You're not wrapping them. How are you really sure that soundness is guaranteed statically? Again, the details are in the paper, so I won't go into that. Okay. Let me talk about sort of future work and questions and open problems and how this relates to maybe things that are more standard, perhaps secure compilation. So the first thing that I want to point out is that the PLDI paper has 3 rather small case studies, right, because it was a framework paper. And what we would like to do is something on the level of interop between ML and Rust. Well, core Rust, we have something called Oxide, formal semantics of surface level Rust, and a core ML compiled to WebAssembly and using the same sort of framework that I've been talking about. That would give us something far more realistic. So that's on our docket. Now I want to talk about the subtleties of the meaning of types. Okay, and I just want to sort of switch to a different pair of languages because I think this will help me easily show what I mean. So suppose you have a pure language. It's just simply typed lambda calculus. It has recursive functions and booleans. I have a stateful language. It's simply typed lambda calculus with ML style references. So type preserving updates allowed. That's it. And it has integers. Okay, so these function types, references here, and that is completely pure, just booleans and functions. Okay, and of course they both have boundaries. What else did I want to say? Outlook load store, that's fine. Okay, I'm going to compile them to the following target language. It's a lambda calculus, and it has fixed because I have recursive functions. But I'm going to give myself this feature of a dynamic region-based memory, which means that there's this new region construct. When you do new region for E, you basically say, I'm going to allocate a new region, and E is going to do all of its allocations, et cetera, reads, writes in that topmost latest region. I also have a memtrap instruction, which basically says trap if the program accesses locations that aren't in the most recent region. This is a little contrived, but I'm trying to make sure that I have the ability to run code that is running only in the most recent region. Once that region is done running, once the scope of this new region ends, I pop that region. And so later on, if I have values left over that are referring to a region that's been popped, I will memtrap, and that'll be an error. Okay, I'm going to use this to catch stuff. We'll get there. Okay, so now let's talk about how, if you were just to sort of turn the crank and try to use this framework, how would you do that? How would you give semantics to these languages? So let's start with what is the meaning of the blue pure types? What do we want it to be, right? So I'm writing this logical relation as P plus S, pure plus stateful languages together. And here's a candidate, right? So we can say that function types are the very standard thing. They're inhabited by target lambdas and a world, and in some future world, you give me an argument, and I plug it in, and I get back a thing of the right type tau, the result type tau. Okay? The interesting part is right here. Do I have it highlighted? Yes. This target code behaves like that blue type tau, pure type, right? If you give me some store or heap that satisfies the world, and I run, etc., then at the end, I end up with some value that behaves like tau in that future world. But this is the meaning of a pure type. What this is saying is that pure types are stateful. It's allowing them to be stateful. So if you just sort of naively write this, thinking about the stateful language, then you've ended up giving the pure types the same meaning. Now both are stateful. And you might say this is okay because maybe you have some big code which is of pure type, and embedded inside it somewhere you're trying to use some stateful code. That's what interop is, right? Okay, so from that perspective, this seems fine. But you've lost the fact that the pure type should be pure. Do we want that? Right? So here's another candidate. I'm still calling this P plus S, but I'm going to try to do a little better. Here I've said, yes, you can go ahead and run in a current store. And while running, your store can change just like it can over there. That's fine. But then at the end, the value that I got, this E prime, it must be a value of the blue type in the old world, in the original world W. It can't pick from a new, more extended world. So it can't rely on new references that might have been allocated during that time. Okay, so it's a bit better. And then here, let's compare it to the obvious meaning of pure types, right? This is a logical relation which you would define if you only had a pure language. You would say, yeah, this pure type, let me tell you what it means. Even if there is a store at the target level, sure, you can run with it, but I never care. My model doesn't even have worlds, right? It never needs to talk about locations because these terms will never refer to them. Okay, so how do we sort of, decide what we want? How do we get code to interact? That's kind of what I want to jump into next. Okay, so again, suppose that you have a whole bunch of pure code. Somewhere in there, you want to put a blob of stateful code. So presumably, what we want is we want to be able to put the stateful code in a boundary and then be pure on the outside again, right? So how do we do that? In order to do that, you need some sort of a mechanism for safe encapsulation of the foreign behavior, right? The foreign stateful behavior. And whatever, like that encapsulation needs to be inserted by the compiler, right? Okay, so let me try. So here we have some target code that's of orange type, it's stateful. And we're trying to convert it to some pure type. I'm writing this for conversion that I wrap around expressions, and I'm writing this kind of cast-like thing for conversions that I wrap around values, but morally, you can squint and think they're the same thing. Okay, so what am I going to do? I'm going to use this new region construct that I have in my language. And again, this is a very simple, contrived thing that I added to my Lambda calculus. When you go implement actual compilers, you have to think about how to implement them at the target, these kinds of encapsulation mechanisms at the target level. But here what I'm trying to do is I'm saying that I'm going to run the stateful code, but I'm going to run it in its own region. At the end, that region will get popped off, right? Which means that whatever value I have left, the x, if it is referring to any locations that are in that region, then this cast will, will essentially get an error. We'll get a mem trap at some point if you try to use it. Okay, so that ends up encapsulating. Gives you encapsulation of foreign behavior. And once you use this particular mechanism for this kind of conversion, then you can prove that, that the logical, that if some expression is stateful and has orange type, then after wrapping it in the conversion, this one, it ends up satisfying a blue type, the one that said that it's pure. Furthermore, you can even prove this lemma, which says that if you have some expression that behaves like a pure type, right? Pure types are not stateful is the meaning of this that I'm assuming. Then you can show that that expression, throw the world away, still belongs to the completely pure, absolutely simple logical relation. So this works out and gets you down to the very simple one, right? So we've shown that like you're really getting encapsulation of behavior. But encapsulation of behavior is great, but you know, in terms of for practical reasons, is probably not the end of the story. Maybe I should pause here just for a second. Any questions? Is this in the same part of the room? Okay.
Does this mean that the pure code and that
Sorry.
that the code around it do not use the same memory locations, or?
Yeah, I mean, it's a contrived example because I'm trying to show you a hard, you know, but small case study. But yeah, it's kind of saying that after I'm done running some stateful code here, where I might allocate, then read, then write, then do whatever, right? Like, and do this with a bunch of locations. They might all have interactions. Then after I'm done with that, whatever value I return will not be a reference. It'll or contain a reference in it. It will have to be a pure value, and it better not. If you're going to go off and use it over here, you're going to be fine. Unless it actually was a location, in which case you will memtrap, right? So you're trying to guarantee pure behavior outside of those boundaries or after the stateful code is run and it has give you something back. Sorry.
This is really nice. This is okay.
Oh, thank you.
This is a model for Haskell's ST monad.
This is what?
A model for Haskell's ST monad. It gives you the ability to, because I mean the ST monad is usually presented in the, you know, the correctness of it is slightly hand wavy.
Now there are very good papers that
but it's allocated. Sorry, I am being, blithe there. But it's allocating a region and then doing exactly this trick. So one thing that's different is, if I remember the ST monad correctly, you can actually syntactically still have pointers into a deallocated region. It's just that you have no way of following them safely.
So you get some sort of no way of following them safely. I mean, that's exactly what's happening here, right? You can have them. I can have them left over here, but the minute I try to use them, I will get a trap.
Yes. So building on this, so do I understand correctly that blue tau can affect, like the value that gets passed and wrapped as blue tau can contain a pointer, and I can send it back into an orange blob later on, or so long as there is a reference there, I am trapping?
No, the region has been thrown away. So even if you go back into orange code, you will not be able to use the location.
Okay.
So it's really like, this boundary means that I threw away all the references.
Different orange blobs cannot communicate with each other.
No, and that's my next slide.
Excellent.
So as Marco just said, different orange blobs can't communicate with each other. What's going on? Okay, so what I would like to do instead of what I just showed is something a little bit more sophisticated. We'd like to make use of imported functions, alloc, read, and write. So obviously these allocate state, then read and write want to use locations that I've allocated using alloc, right? So here I'm using, let's say, an alloc, a read, and write, and maybe I have many more sprinkled in there. But I would like, I shouldn't have to write this surrounding code all in the orange stateful language. I want to just use library functions. But now I have a problem, right? Like, if the boundaries are here and here and here, then what I allocate can never be read, according to what I just showed you on the last slide. Okay, so how do we do better? We want to be able to just use these, and then here, keep writing code in my pure language, because that's my host's native language. The other stuff is just, coming from a library. But then how do we reason about that sort of thing? So this is where this idea of linking types, which we had a while back and we've sort of brought back in a different way. So we can use this idea of these augmented linking types where you take your pure language, and clearly this is a situation where even though we're pure here, we want to be stateful here. right? We want to write pure language code, but we want the type system to say that it's okay for us to be stateful. So what I'm going to say is that here we're going to operate in sort of a linking types universe, and the linking types that I want to allow, remember my pure language only had blue types, integer and functions, but my linking types are going to have those two and have references. And again, this is a very simple example. You can do many more sophisticated things. But now I've added a new reference. So I've added linking types, which are an extension to my pure language, because I want to interoperate with these kinds of reference things. And then I need to add one more thing. I need to give the programmer the ability to say that, oh, this entire zone is linking type zone. And at the end of it, I'm going to put a linking types boundary. That is then going to take us to a stateful part, right? Because this is all blue. You need to give the programmer the ability to put those boundaries somewhere, to decide where, you want to go back to pure land. So that's the basic idea. I'm not showing a lot more detail, but essentially the idea is that this is a blue type here. We define a lowering of a linking type to a pure type. This gets lowered, just sort of recur, but this gets lowered to just int. So you throw away references. You're losing information when you go from linking type to pure type. I'm not going to say more about that. And I'm starting to run out of time. So let's try to do one more and then wrap up. I want to talk about open world soundness and security. Marco will be happy here. Okay, so far, I showed this picture earlier, right? We have a semantic IR, which is this orange circle. So notice that what that means is that we are only supporting interop of our compiled code with other circles in this, right, in the semantic IR. So only linking with context in that circle. What if we want to link with context outside of that circle, context that are sitting over here, right? And maybe there are a couple of things to say here. One is, how do you get open world soundness? I think open world soundness essentially amounts to robust safety. I think. Need to talk about that. But we've been thinking a little bit more about secure compilation. So, and I'm using that term in a fuzzy sense, but let me explain what I'm after. Suppose that we could prove the following theorem, that any compiled programs that are equivalent in here, in this circle, right, so equivalent in the orange circle, that I can put certain protection wrappers around them. So far, I was only allowing, they were not being protected from stuff over here, right? So now I need to put some additional protection wrappers around them. But if I do that, then if I could prove that they are still equivalent after the protection wrappers in this, in arbitrary context, then I've achieved something that's, if you squint a little, starts to look closer and closer to full abstraction. Only I'm not doing source equivalence is preserved. I'm just doing target equivalence is preserved, right? So here's the maybe, and this is Andrew Wagner's idea. I don't know where he is. There you are. Okay. But I think it starts to get, maybe this is lightweight full abstraction. Maybe it's enough. Maybe we don't need to do all the back translations that we've been doing. Love to hear what you think about it. Okay. Because I think that ought to capture the essence of what we're after in many ways, right? The really, really critical theorems. And yeah, I'll stop there. Okay. Last thing I want to say, backends for semantic IRs. Building these semantic IRs is really, really hard if the gap between the source and the target is very large. So I think, all of this, just like compilers have to be done in multiple passes, I think these semantic IRs kind of have to be done in multiple passes. And I think we're going to need mid-level semantic IRs that can be used to build the higher level ones. So, you can build ones for ML using rich WASM, but build ones for rich WASM using WASM inhabiting the source types. We're doing some for designing. Lucy is somewhere. Lucy has been working on a low-level callback push value that sits on top of, it's a type language that sits on top of LLVM. So hopefully we can do that there. Okay, so that's about all I have to say. I've talked about these semantic IRs that tell you, the meaning of source types as sets of target terms. And I think they provide a foundation for designing and verifying sound. I've talked about sound mostly, but I think also secure language interop. And I think we really ought to focus a lot more in the PL community in general on trying to, bring more principles to language interoperability and making sure our implementations are sound. So thank you.